Now we will examine some classical examples, and the one we saw for the wedding shopping is not a classical DP problem, but it is an easy non-classical DP problem. We will see together now some classical examples and classical problems with efficient DP solutions and with states and transitions that you should be mastering and to use later. Among these problems, we will see maximum 1D range sum, maximum 2D range sum, longest increasing subsequence in this lecture, and next we will continue with the problems 4, 5, and 6. To read this UVA, you will conclude the following abridged problem statement. Given an integer array A with non-zero ints of count n, where n is less than 20k, you have to determine the maximum one-dimensional range sum of A. So this is to find the maximum range sum query between two indices I and j inside the range of the array, inside 0 and n minus 1, where the sum a of I plus a of I plus 1, etc., until a of j is the maximal in this array. So if we approach this problem in complete search algorithm, we have an order of n to the power 3. And you have to try all the possible order of n to the power 2 pairs, and for each pair you have an order to the power n to compute the range sum query. So, and then to pick the maximum. And for n equal 20k, this of course will lead to time limit solution. If you remember, you can recall the segment tree and the binary indexed Fenwick tree lessons, because in these lessons we have some sort of solution to pre-process the array A by computing the cumulative values. A of I is equal to A of I plus A of I minus 1 for each I in the range n minus 1, so that A of I will contain the sum of the integers in the range from 0 to I. And now then you compute the range sum query of ij in order of 1, and this will give you range sum query of from 0 to j equal a of j, and from I to j is equal to a of j minus a of I minus 1, to exclude the one before I, for every I that is positive. But this complete search also will lead to the order of n to the power 2, which is still TL in case of n is equal to 20k. However, this kind of solution is also still useful in other cases, but in the case of this big N, we cannot use it, and that's why we will use another method. So Kadane order of n algorithm is considered greedy either or DP. Let us see it. What does it say? So having an array with positive or negative values, and you want the maximum range sum query of this array, you initialize your sum to 0 and your answer to 0, and for I equals 0 to n, this is the order of n, you sum, you cumulate the elements of the array inside the sum, and whenever the sum is greater than the answer, you keep it in the answer, but if the sum is negative, you put it back to 0. And this is the trick here. Whenever the sum goes down below 0, you put it back to 0. So let us see a small animation about the subject. Let us see the memory state of this array. A 4 minus 5, 4 minus 3, 4, 4 minus 4, 4 and minus 5, with the index going from 0 to 8. And we have the three variables, sum initialized to 0, answer initialized to 0, and I, which is going to be used inside the loop from 0 to n. So for I, let's go for I equals 0, we will put inside sum the value of a of I, which is 4, and the answer will take it again because it is greater than its value. For I equal 1, we will put inside the sum 4 and add to it minus 5. It will become minus 1. Answer will not take it, and the sum will become 0 because it is less than 0. For I equal 2, we will add to 0 the value 4, and it is not greater strictly than the answer, so it will not take it. It will keep its 4 value. For I equals 3, we will add 4 minus 3 becomes 1, and for I equal 4, 1 plus 4 becomes 5, and this time the answer will take the value of sum. And for I equal 5, 5 plus 4 equal 9, which is greater than 5, so answer will take this value, answer equal maximum answer and sum. For I equal 6, 9 minus 4 becomes 5. For I equal 7, 5 plus 4 becomes 9. For I equal 8, 9 minus 5 becomes 4. And here I equal 9, and we go out of the loop, and this will finish the problem. So inside after the loop, we will still have our final answer, which was the maximum range sum query of this one-dimensional array, and this is calculated in only order of n. The key idea here was to keep a running sum of the integers seen so far and greedily reset this running sum to 0 if it dips below 0. Why? Because restarting from 0 is always better than continuing from a negative running sum. So this is the key idea. Who is Kadane? Kadane, Joseph J. Born Kadane, is the Leonard J. Savage University Professor of Statistics. He is still alive and doing his job. He is emeritus in the Department of Statistics and Social and Decision Sciences at Carnegie Mellon University, and he is one of the early proponents of Bayesian statistics and particularly the subjective Bayesian philosophy. If you see his CV, you will be amazed. And this problem can also be viewed as a DP solution. At each step, you have two choices. Either you leverage the previously accumulated maximum sum, or you can begin from a new range as we have stated before. So the DP, the state will be I, and it will represent the maximum sum of a range of integers that ends with this I. So until I, every time, if you can see, every time we have the maximum sums of the range that ends with this I. And the final answer is the maximum overall values of dpi, which is for I between 0 and minus 1, which is here inside the variable ans. If you have a zero length range that is allowed, so 0 must be considered as a possible answer too. The implementation of this method is very efficient and utilizes space-saving trick. So let's use this method in solving our problem. In the problem statement, let's go back to the problem statement to see it by title. So in the problem statement, they told us that we have the roots and the output must be for each root inside the input file your program should identify the beginning bus stop I and the ending bus stop J. So they not only want the maximum, they don't only want the maximum sum, they also want the beginning index and the ending index of the sum. So what did we do here in plus of the Kadane solution? Whenever we reset sum to 0, we are saving the index in a temporary variable, and we are using this temporary variable because in the given also they wanted for equal for two possible optimal solutions, choose the one with the biggest difference between j and I, and if there is two same differences, choose the one with the smallest I. So we implement the solution here. We put for if you have an equal answer, if you have a bigger sum, then take this sum, or take this answer again if you have a bigger difference. Then in this case you put the temp to the start variable and the current I to the end variable. And then you print the requested sentence. The nicest part of the root, number of the root is between the start and end, or you can print the root has no nice parts if the sum is negative. So this is the problem, and here is the output of the test case with 3 possible roots. For the first, we have the root 1 is between 2 and 3. The nicest part of root 2 is between 3 and 9, and the nicest part for root 3, there is no nice parts. Another problem is a similar problem, but this time over two-dimensional range. In this kind of problem, you have to return the maximum 2D range sum. And one example of this problem is the UVA 108, which is called also maximum sum. And a problem that is that is simple to solve is one-dimensional is often much more difficult to solve in the two-dimension. And consider satisfying a Boolean expression in conjunctive normal form, which is conjunct consists of exactly 3 disjunct. This problem 3 set is NP-complete, blah blah blah. Given two-dimensional array of positive and negative integers, find the subrectangle with the largest sum. So in here we have two-dimensional array, and instead of finding the largest sum over 1D, we want the subrectangle with the largest sum. The sum of a rectangle is the sum of all the elements in that rectangle. In this problem, the subrectangle with the largest sum is referred to as the maximal subrectangle. A subrectangle is any continuous subarray of size even 1 to 1, okay, even it can be one element or greater, located within the whole array. As an example, the maximum subrectangle of this array is this one. So we are asked to give the maximum sum 2D range sum, and the abridged problem statement is given n times n square matrix of integers a, where n is less than 100, and where each integer inside this square matrix is inside the range 127 minus 127 plus 27, you have to find a submatrix of A with the maximum sum. Example of the paper. This is the maximum submatrix with the maximum sum of 15. If you add the values of any chosen submatrix inside this matrix, you will not have more than 15. So how do we solve this problem? We begin by thinking, of course, how we learn. We learn that we think of the complete search. If the overall time complexity of the complete search solution is acceptable, then we go and we implement it. But here the complete search solution is in the order of n to the power 6, and where n is 100, even for this small n to the power 6 is big. Why n to the power 6? Because we have two loops in order to find the start of I and the start of j, the starting index of the line and the starting index of the column, and another two for loops to find the ending indexes, and then for each rectangle that is chosen, in order to calculate the sum, you have also two additional loops, which makes 6 loops, and this is where O of n to the power 6 came from. And this will exceed the time limit. We can extend the solution that we just saw for the maximum 1D range sum, properly apply inclusion and exclusion principle. So we will use it, but we will properly apply the inclusion and exclusion principle in order to deal with overlapping submatrices instead of overlapping subranges. So what will we do? We will turn this n times n input matrix into a cumulative sum matrix, where A of ij will be equal to the sum of the submatrix of 0, 0 to ij. So, this is our initial matrix. We will produce another matrix which is cumulative. For the value 0, 0, the cumulative is also the same value, 0. And for this, from 0, 0, 0 to 0, 1, the cumulative is also the same, because it is minus 2 plus 0, minus 9 plus minus 2 plus 0 will give us, minus 7 minus 2 will give us minus 9, and then 0 minus 7 minus 2 plus 0 will give us minus 9, and the same thing here, 9 plus 0 equal 9, minus 4 plus 9 equal 5, and then minus 1 plus 5 equals 4, and here the same thing. The sum of this submatrix is 0 minus 2 plus 2 plus 9 equals 9. And we shall continue the animation to see that in this value here we have the submatrix 0 minus 2 plus 9 plus 2 minus 4 plus 1, or in another way, it is the value 9, the cumulative 9, minus 4 plus 1, which is minus 4 plus 1 in the original matrix, which is minus 3. It gives us 6. Again, here we continue the same spirit. We have, for example, the value minus 6, but it must be cumulative with the value 9, minus 7, minus 6, which gives us 2 minus 6, which gives us minus 4, and so on. We fill the matrix, the cumulative matrix. So this can be done while we are reading the input. So in order of n to the power 2, and we can do it like this, while I equal 0 less than, while it is less than n, and for j equal 0 less than n, you scan f the I of a of ij, and if it is a positive integer, if it is not the first row, you cumulate it with the previous value. If it is not the first column, you cumulate it with the previous value of ai minus j, a of I, j minus 1. But if you add the both, if it is not the same, not the first row, not the first column, so you have cumulated the a of I minus j, a of I minus 1, j minus 1 twice, so you retrieve this value one time in order not to calculate double time. So this is the cumulative matrix. What shall I do with the cumulative matrix? The sum of submatrix ij to kl. So this is a cumulative matrix of the submatrix, the sum of the submatrices of always starting from the index 0, 0 to ij. But if you want any submatrix from ij to kl, how do you calculate it? You can calculate it in the order of n. Example, let us suppose we want to calculate the sum of the submatrix from index 1 to 233, which is this submatrix, which is this blue submatrix. How do I calculate this sum? It is minus 6 plus 2 minus 4 plus 1, 0 minus 2, but I don't want to calculate it from the original matrix. I want to calculate it in the order of 1. How? It is equal to a of 3, 3, which is this cumulative value, minus a of 0, 3, which is this cumulative value, minus of a of 3, 1, which is this other orange cumulative value, and because I subtracted these two, I have to add a of 1, 0, which is equal to minus 3, minus 9, minus 13, and plus minus 2, which will give me minus 9. And this problem, as you can see, can be solved in the order of n to the power 4, and if n is equal to 100, it is fast enough. But we can find a faster way. So why we said that this problem is solved in order of n to the power 4? Because if we see the code, you have for ij and for k and l, which is the end indexes of the rectangle, and you don't have anymore a double for loop in order to compute the sum. It is computed directly from the cumulative matrix, just like the example we saw. If I is positive, if j is positive, we subtract the a of I minus 1 L or a of k j minus 1, but if they are both positive, we have to re-add the a of I minus 1 j minus 1, just like the example, and the max subrectangle is the maximum that was calculated in these 4 loops. So this is the start coordinates, the end coordinates, and now instead of order of n to the power 2, we have order of 1. Another better yet greedy algorithm that can help us reduce the complexity to the order of n to the power 3, you guessed it, is to use Kadane's algorithm that was for one-dimensional maximum range sum to be used in two-dimensional range sum, and this solution will be in 0 seconds. How do we do? We do like the following. We have to initialize the matrix, but the cumulative matrix will be row by row, will be cumulating only the rows. So for every aij, if the column is not the first, we will cumulate with the previous columns. A of ij plus equal A of ij minus 1. So we will not, just like the previous solution, cumulate over the columns and the line, but only over the columns. And then we initialize the maximum subrectangle always to the most lowest possible sum, which is minus 127 times 100 times 100. And we will double loop for L equals 0, which is the left index, and to L, and of course the right index must be either equal to L, either greater, because the rectangle must begin at the left index L and at the right index R. And for the row, we will apply Kadane. What does Kadane say? You cumulate until it becomes less than 0, then you will reset to 0, because there is no use to accumulating negative values. And so, what do we do? For each L from 0 to N, for each R from L to N, initialize the subrectangle sum to 0, and then for row, you go from 0 to N. If L is strictly positive, if it's not the first, you cumulate with the previous. So the value is the A of row R minus A of row L minus 1, because this will be outside the range of the subrectangle. You go from L to R, and everything before L will be subtracted. Else, if L is not positive, so you cannot go to L minus 1, it is only equal to A of row R. And if you go down than 0, you reset to 0, and every time you take the maximum subrectangle value and you put it in maximum subrectangle. In this 2VA, you only need the maximum value. You don't need the indices from and to row and column indices. So this is an example in order to understand how does this method works. In yellow, we initialize the row cumulative matrix, and then we use Kadanes on rows and restart if negative. And here is the table in order for you to understand how did we proceed. This is L and R. This is L and R pairs. So you go for L equals 0, 0, 0, 0, 1, 0, 2, 0, 3. For L equal 1, you don't do 1, 0, because this is not a left-right value. You continue 1, 1, 1, 2, 1, 3, and then 2, 2, 2, 3, and then finally the subrectangle 3, 3. And from 3 to 3, you have all these possible values. You can take the only one subrectangle with one value, with two values, either 0, 2, 2, 1, or 1 minus 2, etc. So this is where the Kadane algorithm goes into play. He will cumulate the values every time ending at an index. So, for example, we begin left 0 and right 0, and the row is equal to 0, so the subrectangle is equal to A of row R. A of 0, 0, it is equal to 0. And so on. It will equal to 9, it will be equal to cumulated 9 minus 4, it will be equal to 5, and to 4. Let us check this value here. What does it mean? It means if you take only one width rectangle until the index 3, the maximum sum will be 4. Do I have a vector with 4 until the index 3? Yes, it is all this vector. If I take all, 9 minus 5, the sum is 4. This is the maximal, there is no more. Okay, ending with 3. But ending with the index 1, there is 1, which is 9. Because ending here, you can take either 0, 9, either this value alone, and this is the maximum 9. And the same thing, we go to the value 15, for example. Ending here, you have 9 plus 2 plus 1 minus 4 minus 1 plus 8, which is equal to 15. So during this construction of these cases, we found the maximum subrectangle. So as you can see here, 15 is in fact the sum of the maximum subrectangle. And it can be printed as requested by the UVA. As a conclusion about maximum one-dimensional and two-dimensional range sum problems, we can conclude that not every range problem requires a segment tree or a Fenwick tree. However, they are very useful. Static input range related problems are often solvable with dynamic programming technique, and solution for a range problem natural to produce with bottom-up dynamic programming technique, as operand is already a one-dimensional or a two-dimensional array. So the bottom-up technique here was very natural, and you can still write a recursive top-down solution for a range problem, but it is not as natural as the bottom-up. Next, we will see the longest increasing subsequence classical dynamic programming problem. View here the execution of the order of and